This next section is going to focus on different factors that affect the strength of a muscle contraction. So the first thing that can affect how muscles contract is how stretched out is that muscle. So this is called the length tension relationship. The longer that a muscle is stretched out, it's going to have higher length. So here's my graph here. So along the bottom, we can see the length, and this is in micrometers. So over here would be like my muscle is really short. And then over here, I would have my muscle really stretched out. And then on the y-axis, we have tension. So this is my actual strength. So this is how hard you can contract that muscle. That's an A. Okay. And so 1 being the highest strength contraction, and then half of that and down to 0 being I'm not contracting it at all. So this curve kind of looks like a dome. So there's this optimal region. There's an optimal amount of stretch that will give the hardest, strongest contraction. And so that's the optimal resting length at which a muscle can contract with the greatest force. If a muscle is overly contracted already, so down here, our muscle is very short, and we send an action potential and we do all the process of telling the muscle to contract, but it can't really contract any further. So maybe it can only go a teeny tiny distance. It's not going to contract with very much force because it's already pretty much contracted. On the opposite end of the spectrum, if the muscle's really stretched out, then the actin and the myosin aren't overlapping very much. There's only a little bit of overlap here on the ends. And this means that I can't form those cross bridges. And so, again, it's going to contract pretty weakly over here because the myosin just can't pull on the actin. There's not enough surface area for the myosin to pull on. So here we can see in the middle, we've got enough room to form cross bridges, but it's also stretched out enough to give us enough space to really kind of contract in for as far as we could. So this is that optimal resting length. Our muscle tone keeps muscles typically partially contracted. So muscle tone is continual signals from our nerves that keep our muscles slightly contracted. And so our muscles are typically going to be somewhere in this range due to the muscle tone. And so they're not always going to contract with optimal strength. If you stretch a muscle by giving resistance to it, maybe holding on to a dumbbell while you flex your bicep, that might allow you to stretch it out to get an optimal length. A muscle twitch is a contraction. So common term that we're going to use instead of saying muscle contraction is a muscle twitch. They mean the same thing, totally interchangeable. There is a threshold that is needed to generate an action potential. So there has to be a strong enough stimulation to cause contraction. There's also a delay between when the muscle gets the signal at its sarcolemma to when the actual contraction occurs. So upon the bottom of this graph, we've got time. This is probably in milliseconds. And then tension strength. So this would be the actual contraction. Maybe you were measuring this with some kind of tension meter. So the time of stimulation, this is right here. This is when the action potential is being formed at the sarcolemma. This latent period is that period of excitation, contraction, coupling, where the excitement is moving from the sarcolemma to the inside of the cell. The sarcoplasmic reticulum is releasing calcium. And then the contraction is going to happen quickly as the calcium is released and the contraction phase is going to occur. So this is the contraction phase. And then the relaxation happens a little bit more slowly. So you can relate this graph back to the 4 phases of muscle contraction. We've got excitation, contraction, coupling, contraction, and then relaxation. And this is where the sarcoplasmic reticulum is going to reabsorb the calcium. Twitch strength, so contraction strength, how hard a muscle contracts, is not determined by the strength of the stimulus. Muscle contraction for a single motor unit is an all or nothing. So here we've got the top graph. We've got stimulation, and here's the voltage of the stimulation. So this is the strength of the action potential coming down the nerve. So you would do this with a voltmeter. You could just up the amps of the stimulus. What happens is in the first 2, it doesn't cross the threshold. And so these are not going to generate an action potential. So you can see this is part of the same graph. Here's my muscle. No motor units are recruited. Number 3, we're touching the threshold, so it's going to recruit 1 single motor unit there. Because the stimulus is low, it's going to fire 1 motor unit. That 1 motor unit fires fully, but it doesn't fire these other motor units. With a stronger stimulus, it doesn't cause a specific motor unit to fire stronger. What happens instead is we recruit more motor units. A stronger stimulus still, now we're recruiting 4 units. A stronger stimulus still, now we're recruiting 5 units. And then here's the highest stimulus that's going to give us the maximum contraction force, number 7. Because at this point we have recruited the entire muscle. All of the motor units in this muscle are functioning. So if I keep upping this voltage, these are not going to be stronger. This is going to kind of not react and then go up and then plateau, because at this point the entire muscle was already recruited. So here's that contraction strength, and it's just staying the same because the entire muscle was already working here. I can't actually add anything to it. So these contractions only went up because we got more motor units involved. So each motor unit is all or nothing. It's either going to cross the threshold and go, or it's not going to go. And twitch strength can be determined by a lot of different things. How stretched out is the muscle? Is the muscle already tired? So if you just ran a marathon, you probably aren't going to be doing squats at the strength you would if you hadn't been running. Temperature. So a cold muscle is not going to contract as strongly as a muscle that's been warmed up a little bit. How hydrated is your muscle? So if you're dehydrated, you're not going to have as much transport of energy throughout your body. Muscle's not going to contract as well. And the stimulus frequency. So how often the stimulus occurs is also going to contract the muscle harder. So we can see an example of this down here with something called temporal summation. So temporal means time, and then summing means we're adding it together. And this is going to cause something called incomplete tetanus. So in this first example, the stimuluses are right here, here, and here. You can see the stimuli on the bottom. The muscle twitches, relax. It gets to relax fully. It twitches again, relaxes fully, twitches again, relax. So this would be normal. There's no summation here. When we have stimuli really close together, so you can see these stimuli are much more frequent, the twitch happens and then the relaxation doesn't get to finish before the next twitch happens. And so each increase in stimulus, some of these motor units didn't get to relax yet. So the stimulus is going to recruit more motor units, and this is going to make this twitch stronger and stronger and stronger. It will eventually reach a maximum, and when it reaches that maximum, that's called tetanus. As long as the stimulation continues to occur, that muscle will stay contracted. So tetanus is when a muscle contracts and doesn't relax. This can be caused by a tetanus infection, so you should be getting a tetanus shot every 5 years to be vaccinated against the disease. So somebody who actually gets tetanus, this is usually caused by being cut with like a rusty metal, and tetanus causes the body's muscles to contract, and then they don't relax. They're releasing that calcium, but the calcium never gets put back into the sarcoplasmic reticulum, and so it tells the muscle to continuously contract. People who have tetanus can actually die because their entire muscles in their body can contract. You can break a jaw, break teeth, because the muscles in the jaw are contracting so hard. You've probably experienced small bouts of tetanus. If you've ever had a Charlie horse in your leg, your muscle in your calf tightens up really hard and it hurts. And then in order to get rid of it, you actually stretch that muscle out, and that helps relax it. So the reason stretching your foot fixes a Charlie horse is because what you're doing is you're physically pulling the myosin and the actin filaments apart, and that's going to release those cross bridges and allow the muscle a chance to calmly relax. Often with tetanus caused by this, as soon as the stimulation stops, the tetanus would stop and the muscle would go ahead and relax. So take a moment and think about the process of tetanus and try and explain the physiological underpinning, what's happening inside of the actual muscle filament.